This lesson is about filters set for the X-ray tube. The X-ray tube, in order to be used for XRF spectroscopy, has to be filtered. We saw already these things in other lessons. Filter basically is just a piece of metal from copper, zinc, aluminum, molybdenum, tungsten. The filter set I suggest are two. We have this one, it's called routine, and basically is what I call a good for all filters setup. The parameter of the tube in terms of kilovolts, in terms of microcurrent, and in terms of acquisition time are the same across the two setups. I'm using the same kilovolts, 50, the maximum of my tube, to excite the high energy XRF lines of the most heavy elements. Then I'm using as a microcurrent 50, basically the maximum that my tube can afford at that parameters, 50 keV, and then 30 seconds, okay, to have a relatively fast measurement. What I change is the filter set. So the routine filter set over here, I use two filters. So they are here. The first one, the closest to the tube, is a tungsten 0.025 mm tungsten filter. And on top of this one, there is an aluminum filter, 1 mm thickness. Then the other method, the other setup I suggest is to use just one aluminum filter, thickness 0.25 mm. So this one is called low-keV, because the idea is we want to enhance the elemental peaks that are less than about 10 keV. So, for example, copper has the K alpha line at 8 keV. So this method will increase the reading of copper. So in particular in those conditions where there is a tiny bit of copper, so copper is in traces, so we want to enhance this reading. So what I do in practice in this workflow, my workflow, is I do first a preliminary examination using this filter set, so these two filters. Then I remove these two filters and I place just one filter over here to look at those low atomic number elements. So again, it will be copper, but will be mostly for phosphorus, for sulfur, zinc, titanium. I recommend you to go back to this lesson, X-ray tube output and filters. So this is an introduction to how the output of the X-ray tube can be interpreted in terms of the tubes peaks, compton peaks, target peaks, and so on. So definitely go back to these lessons to understand better this process. Our first experiment will be to measure the output of the tube without any filter and with the routine filters in it to start to make a comparison. So let's go in the lab. We have the tube over here, so we want to measure the output of the tube without any filter at all. So we go here, unscrew this one. This is the collimator plus the filters inside over here, and then basically we remove the filter that is right now over there. We leave the collimator without any filter in it. It goes back here, and we want to measure the output of the tube. We use this plate of high density polyethylene. Now we want to measure in the same conditions of the same plate, but with the routine filters set. We unscrew this one, and here on the filters holder, we put first the tungsten filter, goes here, and then we put the aluminum filter, 1 millimeter. It goes here, and we do the measurement. On the back, this is the result. This black one basically is the output of the tube without any filter. Of course, this is the reason why we can't use the tube without any filter, because there are too much lines over this Bremsstrahlung radiation. That is the one that is good that we need. Okay, so there, when we apply the routine filters set, what happens is that now the output is pretty flat, but of course we see we have removed most of the X-ray. You know, there are just a tiny bit compared to what was before. Unfortunately, this is necessary, so we need to really cut off most of the photons using these heavy filters in order to have a suitable output to measure the high energy lines. So for lead, for barium, so toward 20-30 keV. Let's do now the measurement with just the 0.25 millimeter aluminum filter, so the low-keV setup. Let's go in the lab. We do the same experiment, but we want to use the low-keV filter set. We want to use a 0.25 aluminum filter. This goes inside. We are ready to measure the output of the tube, but using the low-keV filters set. The blue one is the output when we have the low-keV filter set, so just one filter. So what we see is that this area is basically until 10 keV, is pretty flat, so is suitable to do the examination because we have no extraneous extra peaks coming from the tube. And of course here what happens is that this area we cannot use it anymore to make measurement because there is this Compton big peaks over here, the peak from the rhodium over here, so they are too much, too intense. But all these X-ray now, we have plenty of them now compared with the routine filter set. So it means that we are sending much more X-ray to do the analysis. So we can better excite the XRF signal from the low atomic number elements. Let's see it in practice. So we do some case where we compare what happens when we use the different filters set. We go back in the lab and we start measuring gypsum in our pigment checker. Gypsum, that is over here in the white pigments, and then we are going to do the ivory black that is over here. These are the results. So on top, the black one is gypsum analyzed with the routine filters set. So what we see here in the gypsum is just the calcium peak over here. Remember, gypsum is basically an hydrated calcium sulfate. So here we have the calcium sulfate plus molecules of water over there. So we see calcium when we do the measurement, but definitely we can't see the sulfur. So we do again the examination, but this time with the low-keV filters, and now we definitely can see the peak at 2 keV from sulfur over here. The scale in these stacked spectra is the same. We really here have a big increase of the signal, okay, so it's much more, and that's what allows us to really detect these low atomic number elements. Now let's move just to another example. We can test ivory black, so a black pigment containing phosphorus, because it's made from bones. We are going to have calcium phosphate. If we can tell the phosphorus, that's useful to differentiate, of course, between a carbon black from plants, and we can distinguish this carbon that is made with burnt bones or ivory. Here we are. These are the results. Again, here what we see is that when we do the measurement with the standard, the routine filter set, we don't see any phosphorus. So we see a tiny bit, this big one, this peak over here is a calcium, of course there is because it's a calcium phosphate, but definitely no phosphorus. We do the measurement with the low-keV filters, and now we start to see the peak of phosphorus over here. Also in this case, the stacked spectra have the same counts over here, the same range, and the y-axis is the same. We use the routine to cover from 10, also with all the way to the high energy, but also we want to use these low-keV in order to be sure that we don't miss sulfur, phosphorus, as we saw in this example.